So we start discussing what are chain isomers. In case if there is any difference in the chain length, we call it as chain isomers. And if the chain length is same, but the position of the groups is different, then that is positional isomerism, right? So I gave you a few examples of which can be chain and which can be positional. Functional isomers, and functional isomers overpowers chain or positional in general. So that means if you have a different function altogether, in that case, we call it as functional isomers. Okay. So in fact, the 1 degree, 2 degree, 3 degree amines are also functional isomers of each other. Okay. Only in the case of a pi bond and a cyclic structure, instead of using the word functional isomers, we use ring chain isomers.
So can you repeat the last
What beta?
ring chain का भी
In case if you have an open chain versus a cyclic chain, but the function I mean there should not be any new function added to it. Clear? So it is only
got it.
between pi bonds versus cyclic structure. Okay, right. Now check out in all these cases if the question is more to do with the number of structural isomers. Draw all the possible structural isomers. So for any hydrocarbon, if the number of structures are asked, the first thing you will do is check out degree of unsaturation. Okay. So in the case of C4H10, what is the degree of unsaturation? See, this is the formula we use, right? Number of carbons plus 1 minus number of hydrogens by 2. So in this case, it is 4 plus 1 minus 10 by 2. So that is 0. So 0 represent there is no double bond that can exist and everything should be straight chain. It cannot be cyclic structure as well. So therefore, there are 4 carbons, which means this is the one way I can put it, N-butane. Or I can keep one methyl like this and make it as, you know, isobutane, or this is the tert butane as well. Okay. So these are the two forms which you can get. I guess this part is understood, everybody. Now, apart of this, we will not be able to get anything else, isn't it? So maximum we can get these two types of isomers. Now notice next one. If you have C4H8, this time if you compare the degree of unsaturation will be equal to 1. C4H8. So one pi bond can be existing. So that means you can adapt one, you know, pi bond, or I can keep one cyclic. Okay. So that means it should be one cyclic ring as well. So if it is one pi bond, how can that be? See, 4 carbons. You can put pi bond here. I can keep pi bond here. These two are the forms I can have. And next, I can keep, a ring, I mean straight chain with a branch here. This is another way at which I can keep. So these three are the ways by which we can keep the straight chain form and a pi bond. Okay, then let's start with cyclic structure. 4 carbon cycle structure will be here, or one cycle structure with a methyl group. These two are the possibilities only with respect to cyclic structure. Okay, so I guess this part is understood. Sorry. Done. Next. So how many total we are getting here? In this case, we will get 5 of them. Okay. Next. C3H6. Okay. Again, how many carbons we have? What is the degree of unsaturation? Degree of unsaturation will be equal to 1. So logic is I can have 1 pi or 1 cyclic. Okay. So three carbons with a pi bond. This is one part we can have. The other part is cyclic structure like this. Done. So these are the only two parts which we can make it, right? So there is no other way I can make one more pi bond or cyclic structure or something. Next one, C5H10. Got it? C5H10. Degree of unsaturation will be equal to 1. Okay. The degree of unsaturation is 1. Now, where all I can make the pi bonds? Check out. Starting with 5 carbon. Always start with straight chain. 1, 2, 3, 4, 5. So in this straight chain, I can make a double bond here, and then you keep on moving that pi bond inside. So these two are the possibilities. Then repeat this by using a chain, 4 carbon this time, 1, 2, 3, 4, with a chain here. I mean with a branch here. Then keep pushing the double bond at various locations. One is here like this, one is here like this, okay, and one is here like this. These three are three different types of pi bonds you can get. And thereafter, okay, thereafter you try to put everything in cyclic structure. So 5-membered cycle, a 4-membered cycle with a methyl group. Then I have a 3-membered cycle. 3-membered cycle with one ethyl group, or 3-membered cycle with two methyl groups, or 2-member cyclic with two methyl groups like this. These three are the possibilities. Clear? Now count the total. So how many we got here? So 2 plus 3, 5. 4 plus 1, 5. So total we have 10 structural isomers. Okay. Next, C5H12. You can see the degree of unsaturation in this case is 0. Okay. Which means everything should be written, without any double bond or so. This is 1, this is 2, and this is 3. Correct. With more branches. Okay. So I can't make anything new other than these three if it is only uh, alkanes. We cannot make any alkenes or alkynes. In that case, these are the only three possibilities. Likewise, if you have 6 carbons and again degree of unsaturation is 1, sorry, here 0. Degree of unsaturation is 0. In that case, I can have 1, 2, 3, 4, 5, 6 straight chain and with one branch, and keep moving the position of that branch, then make two branch and keep moving position of the two branches. Correct. So these three are the possibilities. So how many we got? 5 of them. So in this case we got 5. Here we got only 3. These are the number of isomers. Oh. See the next case now. Cyclic structure of only C6H12. All cyclic structures only. I'm not asking about the pi bond forms of it. So check out degree of unsaturation for C6H12 is 1, which means only one cycle is possible. So we can have first cycle as like this. Then next one being cyclopentane with methyl group. Next one with 4 cyclobutane with 2 methyls here. Keep moving those methyl groups at different location. I will get these 3. Along with that, one ethyl group, we can keep it like this. With respect to cyclobutane, these four you can get. And then we have cyclopentane, we can have one like this. Next one, isopropyl like this. And after that, I can have one ethyl, one methyl, and change their location also. Ethyl and methyl positions are changed, correct? Thereafter, I can have two methyls and one methyl open like this. And finally, I can have all three methyl groups on three carbons. Please check. I have exhausted all the possibilities now. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So total 12 structural isomers. Okay, next one.
Yes. So can you go a little bit?
Sure.
Gan-
Right. See the next one. Find the number of structural isomers of the molecular formula C3H4. C3H4 has degree of unsaturation 2. So when you have 2, it can have two alkenes, right? So two enes or one ine or cyclic plus ene or bicyclo or spiro. Can you see the possibilities? Five different possibilities. Okay, clear everybody? So now let's try to push as many possibilities as you can in this structure C3H4. Starting with two enes. Yeah. So first one, I have to make a double bond and a double bond. This is the first one which it can exist. Second, one ine, right? So alkyne can exist like this, and one cyclic plus ene. So cyclopropane plus ene like this, correct? And obviously bicyclo and spiro does not exist because it do not have sufficient number of carbons, correct? So how many possibilities we got? Three in this case. Now check out C4H6. In the case of C4H6, starting with that, first four we have. So pi bond and pi bond like this, or pi bond and pi bond like this. Okay. So as much as the pi bonds are number of pi bonds are concerned, these two are the possibilities we can make. Next one, triple bond. Okay, like this. It could be at the center or at the terminal part. So two, three triple bonded forms we can get. Okay. Next, cyclic, four-membered cyclic with one pi bond. Similarly, three-membered with one pi bond. So one pi bond could be outside also. One pi bond could be inside also, like this. So these three are the possibilities as much as cyclopropene is concerned. And next, if you have pi here and make it into bicyclo form now, that means I can make like this. Now it has become bicyclo structure. See, these are all the possibilities we can have. Got it? So how many we can get? 1, 2, 3, 4, 5, 6, 7, 8, 9. So total we have 9 structural isomers. Okay. Now in JE in the recent time, this is the most asked question. Got it? In JE, this has been the most asked question. That number of isomers of C4H6. Anybody has a doubt in this cases? Please check. See the next one. Find the structural isomers of molecular formula C3H8O. Now we are entering into the zone of all functional groups. I have one oxygen with a degree of unsaturation 0. Single oxygen with the degree of unsaturation 0 implies it must be, must be alcoholic, alcohol from alcohol or ether forms. Only these two can exist. So that means if you have a three-membered ring with an alcohol form, this is one way, this is one way. These two are the alcohol forms which you can think of. And then we have ether form like this. So this is the ether form which we can have. So total of three uh, degree of unsaturations. Sorry, three structural isomers. Okay. Next, C4H10O. Okay. Here also degree of unsaturation is 0. So therefore, we must have 4 carbons with an alcoholic group, and OH can be changed into various branch positions like this, and with one tert butanol also. Right. This is alcohol part. How about uh, ether? This is one way to keep the ether. This is another way to keep ether like this way. And then we have like this. These are the three ways we can keep the ethers. So how many total we are getting? 7 in this case. Correct? Now, this again, the next part is more important one. Everybody check out C3H6O. This time degree of unsaturation is 1, which means if you have a single oxygen with 1 degree of unsaturation, it can lead to multiple possibilities. The first being aldehyde, next ketone, next ene plus ether, then cyclic alcohol, cyclic ether. These are all the possibilities we can have. Okay. So functionally, so many different type of groups we can get. So notice, for example, aldehyde. So starting with aldehyde, double bond OH at the end if you have. This is the way to represent. So this is aldehyde. Okay. Next one is ketone. So ketone, only one possibility here. One is aldehyde, the other one is ketone. Next one is enol. This is ene plus alcohol, or ene plus alcohol, or ene plus alcohol. So enol are of three kinds we can get. So these three are the enol forms. Next, ene with ether. Ene with ether form. One possibility is we can get. Next one is cyclic plus alcohol. So three-membered ring with OH. So that is cyclic alcohol. Next, three-membered ring like this. Here we can have three-membered ring like this, which is cyclic ether with a methyl group extra like this. Or I can make it as a four-membered ring with cyclic structure. This is another one. You can see degree of unsaturation is 1 in all the cases, but it is covering so many different uh, types of groups here. Now tell me how many different types of functional groups we have here, functional isomers we have. See, this is a different function, different function. So aldehyde is a different function, ketone is a different function, enol is a different function, ene ether is a different function. Cyclic alcohol is also a different function, and cyclic ether is also a different function. So in total, we have 5 different functional groups, 5 different functional isomers here. Okay. So total in this case will be equal to 9. So 3 plus 4 to 5, 5 plus 4, 9. So 9 structural isomers. Everyone, please check the cases. Any doubt you can ask me. Clear? Hmm. See the next one. We need to make different structural amines. Okay, in case if you want to make a different structural amines here. So check out. Degree of unsaturation in the first case, C3H9Na0. Okay, so which means there are three carbons and then there is amine group NH2. And same with three carbons with NH2 here like this. Now I can make it two carbons with one methyl group on nitrogen, or I can make three methyl groups on nitrogen. So how many total structural possibilities? Four. Got it? So this is called a 1 degree, 2 degree, and 3 degree amines. So number of functional isomers which you can get is three different types. So three kinds here, right? So number of structural isomers, how many we can get total? Total is four. Got it? Next one. C4H11 Okay. So in that case, we'll start with primary NH2. Next, that primary, we can continue at different positions with branches like this NH2 and NH2. So what is that we notice? Just the 1 degree amines are four kinds. You can see there are four kinds of 1 degree amines. Okay. Next 2 degree. So NH and like this, correct? Three carbons with NH and methyl, or like this and methyl. And lastly, four carbons. So methyl, methyl, and ethyl. So you can see 2 degree, 2 degree, and 2 degree, and this is 3 degree. Okay. So number of 3 degree ones you can get is one. 2 degree ones we can get it as three, and 1 degree amines we can get it as total four. So number of structural isomers in this case will be eight. These are the possible structural isomers. Everybody, any doubt in the amines case, please check. See the next possibility. When you are trying to make the different number of isomers with alcohols, okay, only alcohols, right? Only with C6H14O you can get 17 different alcohols. With C4H10O you can get 4, which we have derived it already. You can see here. For this we got 1, 2, 3, 4, 4 different alcohols. Like that, if you have C5H12O, in that case we will get 8 different alcohol forms. Next one is about how many different carboxylic acid and esters we can get out of the molecular formula C8H8O2. Okay. Now, first of all, remember, if you have degree of unsaturation 1 with two oxygen atoms, right? If you have degree of unsaturation 1 with two oxygen atoms, then what are all the possibilities we can get? So one possibility is, okay, we still have ketone or ketone plus one oxygen will be alcohol, OL, all. Ketone plus all, or aldehyde plus all. This is the form we can have. Or then we have ene plus all. There are two alcohols, one ene. Or I can have ene plus ether plus alcohol, or ene plus ether, ether plus ether. Correct? And another possibility is simply carboxylic acid. You can have one carboxylic acid part or ethers. Correct? Then because it is degree of unsaturation 1, so it could be cyclic alcohol, cyclic diols, correct? Or cyclic all plus ether, or cyclic diether. So have you noticed so many different possibilities we can get? Just having two oxygens and one degree of unsaturation, so many possibilities we can get. That's why in such kind of question you will be specifically mentioned only one type of or two types of different forms you identify. Okay, so that's the reason why in this question, if you may have noticed, it has been asked only find two kinds. What is that? One is carboxylic acid kind, the other one is ester kind, but it should be benzene derivative. Okay, so let me first identify degree of unsaturation. So degree of unsaturation as per the given question is 8 plus 1 minus 8 by 2. Correct? Minus 8 by 2. So 9 minus 4. So which is 5. So degree of unsaturation is 5. Now have you noticed that when I simply write benzene, you're already consuming DOU4. DOU4 is already consumed because one ring plus 3 pi bonds is done. So if at all you have degree of unsaturation 5, that means there is one more uh, pi bond which is present just above the benzene. And that's where we have to start. So benzene, first I can have benzoic acid. Now the degree of unsaturation is 5. 4 are covered by benzene, one is covered by C double bond O. And this, along with that, we have one extra carbon because total we have 8 carbons. So now you can see 6 plus 1, 7 carbons. So one methyl group is present, which can be located at ortho position, meta position, or para position. So we can get three different forms in it. After that, we are trying to figure out esters. So C double bond O, O and methyl. So this is one form I can get. This is the ester. And the ester can be reverse also. That means like this. Double bond O with benzene on the other side and methyl on the other side. So this is one possibilities which we can have. Or I can also put one hydrogen here like this with a methyl and then benzene on it. So this is other possibilities I can have. So this is also an ester only. Okay. And now I can directly connect with benzene, and on this benzene I can have methyl being present at ortho, meta, or para position. So which means three other possibilities I can have. So now check out how many total possibilities. 3 plus 1, 4, 5, 6. 6 plus 3, you know, how many we have? 6 plus 3, 10. 9. One more possibility of acid which I haven't written. That should be the first kind. Is where you have a methyl between the acid and benzene. So this is one such possibility. So what are we getting? Total total 10 structural isomers. So this is what you must have got it. Please check. Any doubt in this question? This is also a very, very standard J, advanced question. You'll be usually always asked between carboxylic acids and esters. Right. All these cases are finished. Please check the next one. Same logic. Make acid and esters for C4H8O2. C4H8O2. So C4H8O2, if you notice, the degree of unsaturation is only 1. So which means you can have acid ester. Along with that, we cannot have any other pi bond. Extra pi bond cannot be there. Look. So you can see I can make 4 carbon with a acidic form here. Then I can have 1, 2, 3, 3 carbon with an acidic form like this. Okay. And yeah, only these two are the possibilities as much as the carboxylic acid is concerned. Next, their ester form. So 3 carbon with a methyl group here. Next, 2 carbon here like this. I can have 2 carbon with a methyl group here, ethyl group here like this. This is one possibility. Or one carbon here like this with O like this and H double bond O like this. Correct? These are all the possibilities which we can have. So check out how many we have. 1, 2, 3, 4, 5, 6. Okay. So total we have 6 such possibilities. So number of structural isomers are 6 in this case. Next. C5H10O2. Same logic again. Correct. So we can have straight chain part. Then I can keep on rising towards the uh, branches here. So with all the branches possible, this is what are the acids you can get. Next we have esters. So we can have C double bond O with C4H9. Now C4H9 can be arranged in okay, 4 different possibilities, 4 different ways. What are the ways? We can keep it like this. From here it gets arranged, attached, or like this. From here it get attached, or it could be like this. From here it can be attached, or lastly, from here it can be attached. That is directly tert-butyl. So 4 different attachments we can have. Similarly, I can have methyl with double bond O with C3 H7. So this can be arranged in, 3 different ways. It can be arranged in 3 different ways. Okay, sorry, two different ways we can arrange. So that includes one like this. Sorry, 3 carbons like this. 1, 2, 3. Or second one is like this, isopropyl kind. Next, we can have C2H5 double bond O C2H5. Correct. And lastly, we can have C3H5, right, connected with double bond O uh, CH3. So this side again I can have 2 different forms, 2 different ways, because this time again I have C3H7 kind, which I can put it as 2 different ways. So total check out what are all the possibilities we got. We got 4 different possibilities in the first case. which is with acids. These are all the four different forms. Here we got four different forms, so plus 4. Here we got two different forms, so plus 2. Then I have one of a kind, so plus 1. And again two of a kind. So total how many we get? 13. 13 different isomers we can get here. Please check. Right? These cases are clear. See the next one. Make the structural isomers of C8H10O, which are benzene derivatives only. Okay. And out of that, we need to check out how many of them actually give positive metal test as well. That is sodium giving positive metal test. Okay. Now, what do you mean by positive metal test? In simple terms, see, in case if the oxygen is connected with hydrogen, then there will be very high electronegative difference, and which when you react with sodium metal, okay, sodium will be able to release one electron, at least one electron, and that electron can go combine with this hydrogen and give out as half of H2 gas like this. It will be able to give you this half of H2 gas, which means the electron from sodium is helping to release H2 gas from a position which has highly polarized hydrogen. So, which means this is the connection you should search for in all the examples. What are all the connections we can get? Check out. If it is with respect to benzene, so I can have benzene with an OH group here like this, which is phenol. Or I can have a benzene with some methyl, some alkyl group here with then OH connected to it. So which means an alcohol. So in short, we are only searching for phenol and alcohol cases. You cannot have ether cases, so ethers does not give you positive sodium metal test. Okay. So now keeping that into mind, see how many different ways we can get, how many different structural isomers we can get. Let's start with phenol first. So 6 carbons with OH. So 6 carbons are covered. How many are remaining now? We are remained with 2 carbons. 2 carbons means ethyl. So I can keep an ethyl at ortho meta para position, which makes total of 3 possibilities. Next one, I can keep this phenol with 2 methyl groups like this, 2 at ortho. I can keep one ortho, one meta. We can keep one ortho, one para. Then we can have 2 meta like this, and we can have one meta, one ortho here. Clear? Sorry, one meta and one para here. And lastly, if we have one ortho and one meta on the opposite direction like this. correct? So how many such possibilities we are getting? Six such possibilities. Six different positional isomers. You can see these are all positional isomers. And next we have this one, ether with an, sorry, ethyl group with an OH on it. This is one possibility. And this is an alcohol cases. I can get an alcohol case like this on this position here. This is another possibility. So total how many we got here? Clear? So we can have three such possibilities here. Another, sorry, one more possibility I forgot to write is in case if you have methanol here along with benzene, and then we have methyl connected which can be moved around ortho, meta and para position. So this will also have three such possibilities. So total we can have 3 plus 3 6, 6 plus 6 12, 12 plus 2 14. So total 14 possibilities. Total 14 isomers possible. Good. Next one, metamerism. The next type of isomerism, the structural isomerism which we will learn is metamerism. So far, we came across three different kinds: chain, positional, and functional. The fourth one being metamerism. See, in case if the molecular formula is same functional group also, but the difference number of alkyl groups are present on both side of the functional group, then metamerism is observed. Both side of the functional group means what? Which means the functional group should be such that left hand side, right hand side, are how many different connections the functional group can make. There, the number of alkyl groups should be varying, which makes it an important condition that metamerism is only possible with polyvalent functional groups. We must have a polyvalent functional groups. When do we see the polyvalent groups here? Check it out. In case if you have ketone both sides, in the case of ketones only, both sides we can have an extension of alkyl group. Next, anhydride can also have extension on both sides. Next, esters can also have two different groups on the left and right hand side. Then ethers, thioethers, secondary amides we can have, and sulfonate esters. These are sulfonate esters. Secondary amine and tertiary amine. These are all the possibilities. Clear? So let me write down one by one. I would suggest all of you write down as well. What are all the possibilities for, which are all the functional groups which give the possibilities for metamerism? First one, ketone. Next, anhydride. Next, ester. Next, ether. Then thioether. Then 2-degree amide. 2-degree amide. Then sulfoester. Next, 2-degree amine or 3-degree amine. Correct. So these are all the cases where you see the possibility of metamerism occurring. Now, groups where the metamerism does not happen or does not be seen is when you have monovalent functional group. That means functional group are extended only in one direction, not on both directions. You can see these are all extended only in one direction. Cyanide, isocyanide, alcohol, thioalcohol, nitro, halogen, sulfonic acid, carboxylic acid, acid chloride, amides, amines, 1 degree amines, nitroso, triple bonded carbon, double bonded carbon. See, we can say, sir, what about double bonded carbon? Here also there can be an extension here, isn't it? Both sides we can have different number of carbons, isn't it? Metamerism. Okay. No reason alkene does not qualify for that here is because if you have C double bond C, and let's say one group is like this, and then we have something, you know, ethyl here, and then I try to change the number of carbons here like this, isn't it? Sorry, one more methyl group here like this. Now you might say, sir, what about this one? Aren't these two metamers? Because number of carbons with respect to the double bond on either side are different. So this should qualify for a metamerism part here. Okay. I mean, it looks almost the fair deal that these two are the metamers of each other. But if you have noticed this, we already have given a categorization for that in structural isomers. What is that? It is 1, 2, 3, 4, 5, 6 carbon, 1, 2, 3, 4, 5, 6 carbon. Only the methyl group, uh, only the methyl group has a different form. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. So only you can see this methyl has been kept at a different position. So what is this one? It is simply a positional type of isomerism, isn't it? So a name was already given, positional isomerism. So that is why it is not going to be again qualified for metamerism. Clear? Right. And alkanes are not the ones which are considered to be the functional groups in the case of metamerism. Right. Next, check out. Starting with these examples, when you have ethers, left hand side of the ether, right hand side of the ether, we have two carbons and two carbons. If I take one methyl group and put it on the left hand side, now I can have three, or right hand side, I can have three carbons on the right, one carbon on the left. So that makes these two as metamers. So 1 and 2 are metamers. Now notice 2 and 3 cannot be metamers because number of carbons are same on both sides. They could be chain isomers, they could be positional isomers, but definitely not metamers. Similarly, notice 1 and 2 here. In 1 and 2, left hand side I have a phenyl group, right hand side I have cyclohexyl group. See, even if the number of hydrogens are different, you can call it as metamers, everybody. Now, this case, the hydrogens are different. Left hand side, I have C6H5. Right hand side, I have C6H11. Okay, clear? So we can see we have 2, 4, 6, 8, 10, and 11 here. So total C6H11 or C6H5. So number of carbon might be same, but if you change the position of phenyl and cyclohexyl, then these are called metamers as well. Okay. Here these two are definitely metamers because this is ester, this is ester. Here we have 1 and 2. Here we have 1 and 1 across the functional group. Next, here we have 5 carbons, 6 carbons, 5 carbons. Here 5 carbons, 6 carbons. So these two are also metamers. Now here left hand side 3, right hand side 4. Now here 2 and 1, 2, 3, 4, 5. 2 and 5. So that means these are metamers. Got it? Left hand side 1, right hand side 3. Left hand side 2, right hand side 2. So metamers. This is 3-degree amine. In 3-degree amine, methyl, methyl, and this time ethyl. Now keeping this part constant, see this part I am not moving, keeping this part constant. Now count left and right side. Methyl, sorry, 1 and 3. Now we have 2 and 2. So these two are also metamers. Next, in case if you notice the left hand side, we have 7 and 1. Here also we have 7 and 1. Number of hydrogens are also same. 7 and 1. Now, in such case, should I call them metamers? Not, definitely not. Here we use the terminology, these two being, these three being positional isomers. The only difference you will spot here is that the position of the alkyl group is different. It was first at ortho position, then meta position, then para position. Next, notice this ketone. Left hand side we have 1, right hand side 3, left hand side 2, right hand side 2. So these are definitely metamers. But have you noticed something? This is the only case where the uh, the length of the chain is also same. 5 carbons, 5 carbons. Only the position of the ketone is different, which means it qualifies for positional isomers as well. Correct? But remember, in if you have to prioritize between metamers and positional isomers, you will always prioritize metamers first. Okay? Only if metamers is not given in the options, you will go for positional isomer. Okay? If the question is multiple correct, then you will write both metamers and positional. But single correct, you should always give preference to metamers. Okay? Next, check out the uh, case here on the left hand side. Left hand side I have 3, right hand side I have 2. Right here, left hand side 3, right hand side 2. So now what happened? Now you can see 1, 2, 3, 4. Here we have 1, 2, 3. So chain length has been different. That's why these are only chain isomers and not metamers. Because number of methyl groups are, number of alkyl groups on both sides are same. So these are not metamers. So I suppose metamer cases are clear, everybody. Right. See the next one. The next one being ring chain isomers. I told you about that. So here we have same molecular formula, same functional group, but only difference is open and closed chain. So this is an open chain, this is a closed chain. Again, here we have open chains, this is a closed chain. And closed chain could be this way, B, C, D. These are all the possibilities. So AB, AC, or AD, these three are ring chain isomers. Okay. While if you notice BC and BD, these two are chain isomers because number of carbon groups are different here. Here there is a 4 carbon chain, here it is a 5 carbon chain, here it is a 6 carbon chain. All good? Next, here you see this is an alcohol, this is an alcohol part. So this is a enol. So we can see this is en plus ol, and it is a cyclic alcohol, cyclic plus al. But its main functionality has not changed. It is still being alcohol. So the only thing that has changed is pi has become a cyclic. So pi becoming cyclic is what we call it as ring chain isomers. So these two are again ring chain isomers. Right, everybody? Okay. Now, the last part of structural isomers being tautomerism. Tautomerism. Okay. See, what is tautomerism? Tautomerism is a movement of a particular movement of hydrogen, right, between two different positions in a molecule. At two different positions, hydrogen is moving. And because of the movement of hydrogen, the functionality itself is changed. For example, here can you see it is a triple bond. But in case if at all I make one of the hydrogens from here to move somewhere at this position, then it will become a double bond and a double bond. Right? So triple bond has now become a double bond function and hydrogen has made a movement. This movement of hydrogen from one position to a new position is called migration. So if there is a migration of hydrogen and because of which a pi bond is being moved to one position, new position, then we call tautomerism has occurred. Then we say tautomerism has occurred. For example, in the ketone, in case if the next carbon of the ketonic function has a hydrogen and that hydrogen is moving here, then the pi bond is moving here. In that case, this is called enol. So ketone and enol is also making tautomerism. And this phenomena will be much more enhanced or catalyzed in acidic medium or in basic medium. It can be much more analyzed in acidic medium or basic medium. Next. Next, you see, it exists in dynamic equilibrium and it is represented by this equilibrium sign. It occurs in liquid state and gaseous state both. Okay. Now the types of the migration. Notice what is the type of migration we can get. If a hydrogen is migrating between one position to third position, that means where currently hydrogen is present, it is called position 1. From there, it is going to a position where it is a third position. You call it as the triad system. If it is making 1, 2, you call it as diad system. 1 for migration is pentad, 1, 7 is heptad, 1, 9 is nonad. These are all the different systems of migration. Okay. So you can see, for example, this is a diad system where hydrogen is present on carbon, which is first position. The next element is at second position with respect to hydrogen. So now, if this exists in equilibrium, where this hydrogen is found on nitrogen, so then this will become cyanic acid. This will be isocyanic acid. So cyanic and isocyanic acids are tautomers of each other. Okay, let me put that in writing, everybody. So cyanic and isocyanic acids are tautomers and showcase the phenomena of tautomerism. Next one, ketone. This is ketone. This is enol. So you can see this is a keto group. This is an enol group. So in the keto group, the hydrogen from this carbon is migrating to this position. So with respect to hydrogen, this is at position 1. Now this is position 2. This is position 3. So hydrogen is shifting onto 3. That's why it is called a triad system. Okay, triad system. Now our main emphasis should be to understand the keto-enol tautomerism to be much more details. Check out. If you have ketone and enol, both are exist in equilibrium with K equilibrium given like this. So you notice this. In case if you have, the first carbon connected to C double bond, it is usually called as alpha carbons. In case if you have an alpha hydrogen present on it, then we can showcase a keto-enol tautomerism occurring. But what are the conditions? That hydrogen which is present must be on a carbon which is sp3. It must be sp3 carbon only. So these two are the important condition for keto-enol tautomerism. What is it? At alpha position, at least one hydrogen must be present on sp3 carbon hydrogen. Notice this example, for instance. Left hand side I have alpha, right hand side I have alpha hydrogen. But this alpha hydrogen can participate in tautomerism, but this hydrogen cannot participate in tautomerism. So if I were to ask that how many number of alpha hydrogens are present which can show tautomerism, are 2 in this case. So there are total of 2 such cases. Clear, everybody? Right. See the next one. Now the first part that will be asked to you as a question is to identify how many of them are actually giving tautomerism. Okay, which of the following can show tautomerism? See, these are all the compounds given. and I need to figure out which one will give tautomerism. Check out if there is a possibility of alpha hydrogen, which is sp3, right? Now, this we have one possibility. So yes, this can show tautomerism and alpha hydrogen is 1. Here, no tautomerism because alpha hydrogen is 0. Now, this is already a enol form. In enol form, hydrogen is there, one hydrogen. This hydrogen can give tautomerism. So, alpha hydrogen is uh, 1 here. This is the one which can be pulled back here, and double bond O can come here. So, 1. Now, this is an interesting case here. See, here C double bond O, this is the hydrogen which you have where alpha hydrogen is present. But if the alpha hydrogen has a conjugation, that means a resonance which is possible next to that alpha position, because this is alpha carbon, next beta and gamma has a double bond. Then this delta carbon can also show tautomerism as long as it is sp3. So we have total of 3 different hydrogens which can be migrated to convert into enol form. Here, although there are alpha hydrogens, but they are all on sp2 carbon. So hence no tautomerism. So in this case, there is no tautomerism. Similarly, here also, although there is sp3 carbon and hydrogen, everything is qualified here. But this is a special case. Problem is, on the bridge position, it is impossible to make a double bond. So enol formation is not observed. So tautomerism is not observed, even though alpha hydrogens are 2. So have you noticed, is it always necessary? Sorry, only if you have alpha hydrogen, right? Then only it can show tautomerism. Not necessary. Even if you have an alpha hydrogen, yet this is not able to show tautomerism. Next, in this case, if you notice here, I have alpha hydrogen at this location and this location. And how many are there? Hydrogen here, hydrogen here, hydrogen here, and hydrogen here. These are the 4 possibilities. Along with that, is there any possibility on this side? No, this cannot be participated anymore. Clear? Now you might wonder, sir, what about because there is a conjugation here? See, listen, conjugation should always help up to the double bond O, but this pi bond is not going anywhere towards C double bond O. So in that case, alpha hydrogens are 4, tautomerism is shown. Here you can see these 2 hydrogens can show tautomerism. So yes, so alpha hydrogens are 2 in this case. Okay, sorry, 2 and 2 here also. This side also we have 2. So total we have 4. Next. Here there is no alpha hydrogen, so no tautomerism. Here enol is present. In the enol form means this hydrogen itself will undergo tautomerism to give keto form. Next, notice this one. Here these 2 at the center, which are active methylene cases, can give alpha hydrogens. I mean, they can showcase tautomerism. These 3 hydrogens can also show tautomerism. Likewise, here there are 2 alpha hydrogens which can show tautomerism. And here there are no alpha hydrogens, so alpha hydrogens are 0. Here alpha hydrogens are 0. And now here again alpha hydrogens are 0. So no tautomerism, no tautomerism, and no tautomerism. Right. So I want all of you to go through the cases once again. I'll give you a minute's time. Go through it. If you have any doubt, you can ask me. I'll repeat it. Mechanism. We must learn to write the mechanism in all these cases, that how the uh, tautomerism is observed both in acidic medium as well as basic medium. Step by step is important. Okay. Let's see how the tautomerism works. And I'm taking only reference of keto enol. Well, we can make tautomerism in different functional groups. Our main objective as well as what is there in the syllabus is only keto-enol tautomerism. So first using basic medium, check out. Let me take an example of acetone. CH3 C double bond O CH3. So this is acetone. Okay. Now this acetone, when you know keep it in basic medium or add some NaOH or something. Now you'll notice this has C double bond O CH3, and here it will become CH2 minus, correct? And this CH2 minus, right, followed by hydrolysis, correct, will give us CH3OH double bond CH2, which is enol. Okay, this is the enol part. Now see step by step. The first step is when you have CH2H with double bond O CH3, then the OH minus as a base can extract this proton, convert into CH2 minus and C double bond O CH3. Now notice this can undergo tautomerism. See the difference in the symbols, everybody. This is equilibrium symbol. This is the resonance symbol. So we will get this as CH2 double bond C because you are pushing the electrons away towards oxygen. So we get this as O minus and CH3. And right, so this is about step 1. So step 2 is all about CH2 double bond C, O minus and CH3. Please notice one thing. This type of structure is called as enolate ion. So it will be enolate ion. Next. So this is the enolate ion. And this, when you treat with water, it will take H plus and convert itself into CH2 double bond C, OH and CH3. So what we get here, we got this as enol part. So we got this as enol. So we started off with ketone, we ended up at enol. The converse should also be true now. So that means if you start with enol, we should be able to end up at ketone. So CH2 double bond C, OH and CH3 is present. Now that when you treat with OH minus, this OH minus can extract this H plus and it can make it as CH2 double bond C O minus and CH3 minus H2O because it has lost H2O form. Now again this can show resonance stabilization as CH2 minus C double bond O and CH3. Okay, and from here if at all we treat this in H2O, so it can take H plus from water, convert into CH3, C double bond O CH3. So you can clearly notice that from the enol form, we went all the way up to ketone. Okay. So you can see it works on both sides. Enol to ketone, ketone to enol. So please check basic medium, everybody. All okay. Everybody has written that. Right. Now let's notice this in acidic medium, everybody. How does tautomerism work in acidic medium? See, we start again with ketone. The first step, show the keto part here. So CH2H, I'm writing it this way. And when you have H plus present, right, that means the lone pair of this oxygen is the first one to attack that H plus. So it will have OH plus and CH2 and H. This is the first part you can get. The first step is called protonation because you are taking a proton on oxygen. This is called protonation. The second step is, I have a double bond H plus and CH2 and H is present. And now this bond is broken by carbon hydrogen to this as support this as OH group here. So in that case, we can see this as OH with a double bond here and one uh, H plus is being lost from here. So the H plus being lost is called deprotonation. So it went to through these two steps. One is protonation, the other one is the deprotonation. So in this case, we got this as the enol part. Have you noticed, unlike in the first case, there is no enolate ion formation, directly ketone to enol or enol to ketone that will happen in the case of acidic medium. Now see the converse, the reverse of it. That is, in case if you have an enol, correct, and that when you treat in acidic medium here, so that is with H plus here, the lone pair on oxygen present will be pushed pi bond here. The pi bond will move here, and this negative charge will take H plus from here. So what are we getting? Double bond OH plus, correct? And on this position, we are getting H plus. So in this case, the protonation is happening, but on oxygen position here. Okay. And next, the fourth step being, once you get this double bond OH plus and H here, it will lose out this H plus because it is a part of the solution itself, plus H plus. So this will become ketone and H plus. So this is deprotonation. So protonation and deprotonation is being followed in acidic medium. Either you start with ketone towards enol or enol towards ketone. Okay. Now, general funda is generally, if you compare the rate of tautomerism, then you will notice that basic medium will have faster rate compared to that of acidic medium. In basic medium, tautomerism happens at a much faster rate compared to that of acidic medium. Everyone clear? Now, next notice, what are the factors that influence the percentage of enolization? That means whether the enol amount is more or less depends upon what factors. The first one being resonance and conjugation in the enol. If there is any resonance or extended conjugation is observed in the case of enol, that will influence the percentage of enol. Second one is intra-H bonding. In case if there is any intra-hydrogen bonding established. Nature of the solid, whether it is polar or non-polar or aprotic and so on. It is acidity of enolic hydrogen. If the hydrogen is much more acidic or less acidic, that depends. Then you will notice normal inductive effect and steric factors, okay, which we usually check it out, correct? Next, aromaticity. By chance, if there is any aromaticity observed, then also it will change the rate of enolization. Next one, temperature and phase of the compound. So what is the temperature at which you are operating and whether it is in liquid state or a solid state. These will also influence the rate. All these cases has been asked as multiple correct questions. So you should know what are all the factors rate of enolization depends on. Clear? Now, let's notice this one. When it comes to ketone converting into an enol, what exactly in the mechanism, which bonds are actually breaking? Just check it out. In the case of ketone, C double bond O has a bond energy of 179. That is this one. And then CH bond, this one, CH bond has around 99. And C single bond C has a bond energy of 83. Yeah. Okay. So imagine like this. We are basically breaking this bond, and this bond. And what are we trying to make? We are trying to make one OH bond. We are trying to make one CC double bond. And we are trying to make one CO single bond. Okay. So imagine as if you're breaking all these bonds and you're making all these bonds. And while making this much energy is released, but for breaking this much energy is required. What is that we notice? We notice that there is 18 kilocalories deficit. That means in enol form. So which suggests that given the chance, which side the functional group would like to exist, it will try to be more on the ketone side because ketone side we have a stronger bonds is as compared to that of enol side, which has a relatively ketone to enol. If you compare, ketone has a stronger bonds. Okay, now notice delta H of reaction must be if it is greater than zero. Reactant must require more energy to make into products, isn't it? And if you notice this one, ketone to enol, let's say I'm doing it at room temperature, which is around 300 kelvins. If they exist in equilibrium, delta G is zero. That's the definition. That and chemical equilibrium is achieved when the delta G is zero. That means change in free energy should be zero. And if delta G is zero, we know that as per equation, delta G naught will be minus RT ln K equilibrium. Let's see. We'll try to write two different forms. One is a case where enol percentage is 1. I mean, sorry, ketone percentage is 1, enol percentage is 99. And second case where the ketone is 99% and enol is 1%. So I have substituted that values. First will be 1 by 99. Second one will be 99 by 1. So from here I can say something. Delta G, even if you vary that much, 1 is to 99, the change in free energy is only 11 kilocalories. And notice, if you take it 99 by 1, it is going to come as minus 11 kilocalories. So in short, if I'm able to provide 22 kilocalories of extra energy, I will be able to convert 99% ketone into 99% enol. Alright. So this much is the conversion that you will be able to notice. Hence, if hydrogen bonding is obtained, suppose in enol, there is a hydrogen bonding, intramolecular hydrogen bonding established. One hydrogen bond can actually make a difference of 30 kilocalories. This much amount of attraction you can have. Or if an aromatic ring is formed, minimum 35 kilocalories of energy is being released. Which means if you have any of these two cases, you are certain that the enol is in very large quantity, ketone is less in quantity. Now check out what will be the following according to the decreasing order of rate of enolization. Check out the first case. In the first case, there is no alpha hydrogen only. So there is no tautomerism. Here there are two carbons. If you make a enol form, this is the enol which you will get. And in this case, phenyl can participate in resonance here. This phenyl can participate. So huge resonance, right? That is what happens in the case of 3. With only one phenyl, you will have relatively less resonance here. So which one has more rate of enolization as well as the content? So it is 2, then 3, then 1. So that is the rate of the reaction. Rate of, sorry, enolization. First case is clear, everybody. Check out the second case. In the case of second one, here, this carbon is active methylene. Active methylene, if you make it as minus charge here. So let me just take all of this together. Now notice, in all these cases, I'm supposed to make a carbon anion here. Minus, 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 and minus. Now this minus can get conjugated on both directions like this, both directions. While here it will go like this and then C minus. Next here, the same resonance can be observed on both sides, correct? Here also the same thing, resonance can be applied on both directions. Here also you'll have O minus or O minus. Here also CO minus and here also CO minus. Now notice the last two cases. When you actually have OME here, which has a lone pair on its own, so this lone pair is also trying to make a resonance, and that will make a much stronger resonance as compared to that of the carb anion which is forming. Because this carb anion is already splitting into both directions. But here the lone pair on oxygen will be only in one direction. So this resonance will overpower this resonance, which means the ability of making a resonance, sorry, the ability of making a resonance on this direction decreases. Okay, so this direction the resonance will decrease. Similarly, here, because the lone pair present on oxygen, that would make it as C minus. So check out here, same logic here from this end, pi bond is trying to move. And lastly, sorry, this resonance has been stopped on both directions. So here also the lone pair will push like this. So what have you noticed that in the last case we have the worst resonance. This one is still okay, this one is better, much better, this one is much better, and the best is this A form. Okay. So when you have this, remove this H plus. When you remove the H plus, we expect it to migrate. So it will migrate on this oxygen. So this is that form, and this is the enol form which we have developed. Enol form. Notice in enol what is happening. You can see the lone pair from here is undergoing conjugation. Pi bond is pushing, this pi bond is pushing, O minus charge is taking H plus. So we got an extended conjugation as well as it has intra-H bonding. Everybody please check. So extended conjugation and intra-H bonding are helping it. Okay. Next one. This side, both of them are helping it, but at the same time, methyls, hyperconjugation will try to, decrease the resonance which is occurring here. So because methyl is offering plus I and hyperconjugation, it will destabilize the extended conjugation. That's why this percentage, although it will be sufficiently high, now this carbon's double bond and hydrogen will not make us very strong bond. Okay, next one. Here we have, yeah, here you can have this oxygen already making a resonance of its own. So no tautomerism required. And here also it can make on its own. And methyl group is present. So that means there will be some amount of donating nature. Hence, this group will have destability due to methoxy groups. Okay. Second case is clear, everybody. So in case if at all I have to produce the, if at all I have to write the rate of enolization. So check out rate of enolization. So definitely we can say A will have more, then B, then C, then D, then E. Next, please check out the third one, rate of enolization. Okay. If extended conjugation is there or more withdrawing groups are there, that will always help. Donating groups are destabilizing, so tautomerism becomes weak. So you can see NO2 is strongly withdrawing here. NO2 is strongly withdrawing. Methyl is supporting, while cyanide is also strongly withdrawing. So which makes B greater than C greater than A. Check out the fourth one. All okay? Right. See the next one. Rate of enolization in the second case. Here it is the same case here. This is active methylene. Both sides we have ketone. Here we have keto and one ester. Both sides we have diester. Here both sides we have nitrogen. So see nitrogen is much strongly donating group. Hence the order. Order will be A greater than B greater than C greater than D. Okay. Likewise, see the next case. Here if you have already minus charge and if there is a methyl group, that minus charge is destabilized. And third, we do not have any methyl groups on left or right. Here, the minus charge which you will get is a conjugated, resonance stabilized. So therefore, 4 will be much better than 3, then 1, then 2. So this is the order of enolization. Done, everybody? Please check. And check out the last thing. Rate of enolization in this case. We have A, B, C, D here. Same logic here also. There is diketone here. The one is keto ester, diester, and diamines. So diamines will be the least. So A, then B, then C, then D. Okay. This is the rate of enolization. Now, if the question is asked, what about the enol ability, correct? Percentage enol or rate of enol. In acidic medium specifically, it depends upon the stable alkene that it is forming. That enol formation stability is more important. You can see if you get a double bond here, there is no alpha hydrogens. If you have a double bond here, we have alpha hydrogens. And if you have a double bond here, so we can have the more number of enolization occurred. So therefore we can say C, then B, then A. That will be the rate of enol, enol form. Okay. Finished everybody? Right. So here you can check out. Last thing is about percentage enol content. Okay. So I want you to just go through the first six cases and try to understand the reason in all these cases. What is the reason for such enol content? First case, this is ketone, this is enol. Generally, ketones are more stable because of thermodynamic factors. Thermodynamic factor. Next, between these two. Right, next one. Next one, you check out the number of alpha hydrogens here. Okay. So, but still this is ketone and this is enol. So it is still going to exist in traces. So this is become because of the same thermodynamic factor conditions. Third one. Third one again, it will mainly exist on the ketone side. Hardly you will see enol content is because of anti-aromaticity raised in enol content. Anti-aromaticity in the enol form. See the next one. Now this time it is 100% enol because phenol is an enol of this one. Right. Next one. You can see here it is getting aromatic nature. That's why enol is aromatic. Next one. Check out in this case also the logic is the same. It is getting aromatic plus hydrogen bonding. Intra-H bonding. Next. In this case, earlier the lone pairs were repelling strongly, which had more amount of repulsions. So what are we doing? We are minimizing torsional repulsion, torsional repulsions. Minimizing the torsional strain and new intra-H bonding. And because of the strong infra-H bonding, possibilities are here the enol will be the 100% form. Right, check out in this case. We have here as active methylene, it can make a double bond here, enol, but the problem is these lone pairs will also push the electrons. So the reason is diesters, diester oxygen form can resonance stabilize on their own. Right? Check out. Last one. Why again percentage enol is very less? This is also known as AAE, acetoacetic ester, or EAA, ethyl acetoacetate. In both these cases, the logic is the same. Here, the lone pair will try to push here, pi bond will move here. That will try to decrease the enol stability. Okay, so this is beta keto ester. So this time it is beta keto ester. Next one, you can see slowly how the percentage is increasing. This is the same reasons we have written it earlier. Okay. So you were mainly going to be asked like which one will have more amount of percentage hydrogen, sorry, more amount of percentage enol. Second one is whether there is any tautomerism happening or not, and which case enol percentage is 100%. These are important cases, in which case it will be 100% and which case it will be 0%. Okay, right. Okay. So this is a assignment which I would expect you guys to do it at try it on your own, and then I can discuss in the class.